April 23, 1943. RAF Bomber Command Headquarters, High Wycombe, England. The room smelled of stale cigarette smoke and desperation. Wing Commander Roberts slammed his fist on the mahogany table, sending aerial reconnaissance photos scattering across its polished surface. "You want us to trust our bomber crews to strips of aluminum foil?" His face had gone crimson. "That's the most insane thing I've heard since this bloody war started." The man standing before him wasn't a decorated officer. He wasn't a Cambridge physicist or an Oxford engineer. Joan Curran had no engineering degree, no formal military training, just a failed job application from the Royal Aircraft Establishment that still stung 3 years later. They'd called his ideas impractical, too theoretical, not grounded in reality. But what Joan Curran created in a cramped Welsh laboratory would save thousands of Allied lives, cripple the Luftwaffe's most sophisticated defense system, and change aerial warfare forever. The German High Command would spend millions trying to counter a weapon that cost pennies to produce. This is the story they don't teach in history class. The story of how a rejected engineer turned the Nazis' greatest technological advantage into their most catastrophic vulnerability. Stay until the end, because what happened next shocked everyone, including the German radar operators who watched their screens turn into meaningless static. The spring of 1943 was a season of death in the skies over Europe. Every night, RAF bombers thundered across the channel toward German industrial targets. Every night, fewer returned than had departed. The mathematics were brutal and unforgiving. Harris's bomber crews faced a 70% probability of death before completing their tour of duty. 70%. Not because of German fighters, though they were deadly. Not because of anti-aircraft guns, though they filled the sky with explosive steel. But because of something invisible, something that tracked bombers from the moment they crossed the coast until the moment they either dropped their payload or fell burning from the sky. The Germans called it Würzburg. The British called it a nightmare. German radar stations dotted the European coastline every 12 miles, giant dishes that could detect a bomber formation at 60 miles, guide night fighters to within visual range, direct flak batteries with terrifying accuracy. The technology was brilliant, precise, unstoppable. British losses climbed week after week. In March alone, Bomber Command lost 140 aircraft in a single operation over Berlin. 140 crews, 980 men who climbed into their Lancasters and Halifaxes, knowing that German radar would find them, track them, kill them. The medics were overwhelmed. The morgue details worked overtime. Station commanders stopped learning the names of replacement crews. Squadron leader Davies stood in the briefing room at RAF Scampton, watching fresh-faced boys try not to show their terror as the intelligence officer marked the night's target on the map. Hamburg again. The fourth time in 2 weeks. Davies had flown the first raid. He'd watched the radar-guided searchlights catch Jenkinson's Halifax in their cone. Watched the flak find it within 30 seconds. Watched it spiral down, trailing fire and screaming men. The problem wasn't lack of courage. British air crews had courage in abundance. The problem wasn't lack of firepower. The new 4,000-pound blockbuster bombs could level entire city blocks. The problem was that every bomber was a flying target, lit up on German radar screens like a Christmas tree, tracked from the moment of takeoff to the moment of destruction. British scientists tried everything. They varied approach altitudes, hoping to fly below radar coverage. The Germans simply adjusted their frequencies. They experimented with rubber coatings on aircraft fuselages, hoping to absorb radar waves. It made the bombers heavier, slower, and didn't reduce detection range by even a single mile. They attempted coordinated jamming equipment, massive transmitters that weighed hundreds of pounds. The Germans adapted their systems within weeks. Every solution failed. Every field test disappointed. Every theoretical breakthrough crumbled against operational reality. The losses continued. The crews continued dying. The strategic bombing campaign that Churchill and Roosevelt had promised would break Nazi Germany was instead breaking against the wall of German radar technology. Senior commanders began questioning whether the offensive could continue at all. The mathematics were simple and terrible. At current loss rates, Bomber Command would cease to exist as an effective fighting force within 6 months. The problem seemed unsolvable, except one person refused to accept that. Joan Curran was not an engineer. He had no formal degree in electrical systems or radio physics. Before the war, he'd been a schoolteacher in Cardiff, spending his weekends tinkering with radio equipment in a garden shed, building crystal sets and primitive transmitters. He'd applied to the Royal Aircraft Establishment in 1940, hoping his radio experience might prove useful. The rejection letter was polite but firm. "We require candidates with formal qualifications in electrical engineering. Your application does not meet our minimum standards." So he'd taken a position at the Telecommunications Research Establishment in Malvern, filing reports, organizing equipment inventories, doing the unglamorous work that kept the research facility functioning. He watched the brilliant scientists, the Cambridge men and Oxford fellows, as they wrestled with the radar problem. He listened to their discussions in the cafeteria, their frustrated arguments about wavelengths and reflectivity and signal propagation. And he watched the loss reports come in. Every morning, the casualty figures from the previous night's operations. Every morning, another page of names, another column of aircraft that would never return. May 14th, 1943. Curran stood in the TRE courtyard during his lunch break, eating a cheese sandwich that tasted like sawdust, watching a maintenance crew work on a radar array. The spring sun caught the aluminum framework, making it flash and sparkle. Something about that flash triggered a memory from his childhood, summer afternoons near Cardiff, watching sunlight reflect off the Severn estuary, how the water's surface could scatter light in 1,000 directions at once. Something clicked in his mind, a connection so obvious he felt foolish for not seeing it earlier. The problem wasn't that German radar was too powerful to jam. The problem wasn't that British bombers were too reflective to hide. The problem was that everyone was thinking about the challenge backward. You didn't need to make bombers invisible to radar. You didn't need to jam the radar signals. You needed to give German radar operators so many targets they couldn't tell real bombers from false ones. You needed to blind them with noise, drown their screens in phantom contacts, turn their sophisticated detection network into useless garbage. The challenge was creating something that reflected radar waves as strongly as a 4-engine bomber but weighed almost nothing. Something you could drop by the thousands from aircraft without affecting their performance. Something so cheap to manufacture that losing 90% of them wouldn't matter because you could simply make more. Curran went back to his desk that afternoon and pulled out the notebook he always carried, the one with the cracked leather cover and pages filled with his cramped handwriting. He began sketching, calculating, working through the physics in his methodical, self-taught way. Radar waves were just electromagnetic radiation, like light waves but with much longer wavelengths. The German Würzburg system operated at 53 centimeters. A metal surface would reflect those waves, but the reflection strength depended on the surface size and orientation relative to the incoming wave. A bomber reflected radar waves because of its large metal surfaces, wings, and fuselage acting like mirrors. But you could create an artificial reflector, a piece of metal cut to specific dimensions that would resonate at the radar frequency, reflecting the signal back toward its source. The physics were straightforward. The engineering was deceptively simple. He worked late that night in his cramped office, the only light coming from his desk lamp and the red glow of his cigarette. His hands trembled slightly as he drew, not from cold, but from the growing certainty that he'd found something real, something that might actually work. The critical measurement was simple. Strips of aluminum foil, cut to exactly half the wavelength of German radar, 26.5 centimeters, about 10 inches. Bundle them together, and each strip would act as a dipole antenna, reflecting radar energy with an efficiency that seemed almost magical. Drop enough of these strips from a bomber, and the German radar screen would light up with hundreds, thousands of false contacts. The operators would be overwhelmed. Their sophisticated tracking systems, their precision targeting, their carefully calculated interception vectors, all of it would dissolve into meaningless chaos. The breakthrough came at 2 a.m, calculations spreading across 3 pages of his notebook. He stubbed out his cigarette and allowed himself a small, tired smile. It would work. He knew it would work. The physics didn't lie. Now he just had to convince everyone else. The next morning, Curran requested a meeting with the facility director, Dr. Robert Cockburn. He brought his notebook, his calculations, and a small prototype he'd cut from a roll of aluminum foil meant for the facility kitchen. Cockburn listened with the polite patience of a man who'd heard dozens of impossible proposals. When Curran finished his explanation, the director leaned back in his chair and sighed. "Joan, I appreciate your enthusiasm, but this is rather outside your area of responsibility. We have trained physicists working on radar countermeasures." "With respect, sir, those trained physicists are trying to overpower German radar with brute force jamming. I'm suggesting we outsmart it instead." "With tinfoil." Cockburn's tone made it clear what he thought of the idea. "You want me to present to Air Ministry that we can defeat the Luftwaffe's most advanced technology with the same material we use to wrap sandwiches?" "Not defeat it, sir. Confuse it. Overwhelm it. Turn their strength into a weakness." Cockburn dismissed him, but Curran wasn't deterred. He spent the next week building a proper prototype, working in the facility's machine shop after hours. He cut precise strips of aluminum, each exactly 26.5 centimeters long, bundled them together with cotton thread into small packets. He calculated drop patterns, dispersal rates, how many packets would be needed to saturate a given volume of airspace. He showed his work to younger researchers, the ones fresh from university who hadn't yet learned to dismiss unconventional ideas. Word spread. Someone mentioned it to a visiting liaison officer from Bomber Command, who was desperate enough to consider anything. 2 weeks later, Curran found himself at RAF Bomber Command headquarters, standing before a panel of skeptical officers who looked at his aluminum strips with barely concealed contempt. Wing Commander Roberts was the most vocal critic. "You expect us to risk multi-million-pound aircraft and highly trained crews on this nonsense? These strips will be torn apart by prop wash before they even leave the aircraft." "That's the point, sir. They need to disperse, create a cloud of reflectors." "And what happens when German radar operators simply ignore the false contacts?" "They won't be able to tell which contacts are false. Each of these strips reflects radar energy with roughly the same strength as a medium bomber. Drop 50,000 of them, and the German screens will show 50,000 bomber-sized contacts." The room fell silent. An air vice marshal leaned forward, studying the strips Curran had laid on the conference table. "How much does each packet weigh?" 40 grams, sir, about an ounce and a half. "And they can be dropped from existing aircraft? No modifications needed?" "None, sir. They'll fall through the bomb bay or can be pushed out of flare chutes." The Air Vice Marshal looked at Roberts. "We're losing 50 bombers a month to radar-directed defenses. If there's even a chance this works, we have to test it." What happened next changed everything. The test was scheduled for the night of July 24th, 1943. The target was Hamburg, Germany's second-largest city and a critical port. RAF Bomber Command would launch Operation Gomorrah, the largest aerial assault of the war to date. 791 bombers, and for the first time, they would carry Curran's aluminum strips, now codenamed Window for security purposes. The packets were loaded aboard the bombers in wooden crates, thousands upon thousands of them. Each Lancaster and Halifax carried 2,000 packets. Simple, cheap, elegant. The aircrew were briefed to begin dropping Window as soon as they crossed the German coast, one packet every minute, letting them scatter through the prop wash and disperse across the night sky. Squadron leader Davies sat in his Halifax's cockpit, watching the sunset paint the English countryside gold and crimson. In the bomb bay behind him, alongside the high-explosive ordnance, sat 40 crates of what looked like Christmas decorations. He'd lost 60% of his squadron over the past 3 months. If tinfoil could help even slightly, he'd happily carry it to Hamburg and back. The bombers lifted off at 2200 hours, a seemingly endless stream of aircraft climbing into the darkening sky. They formed up over the North Sea and turned toward Germany, engines rumbling, wings heavy with fuel and bombs and hope. The first packets of Window went out at 23:30 hours, just as the formation crossed the Dutch coast. Wireless operators pushed them through flare chutes, watching them tumble away into the darkness. The aluminum strips caught moonlight as they fell, glittering like snow. 50 miles away, at a Würzburg radar station near Bremen, Lieutenant Schneider sat at his screen, watching the familiar pattern of incoming British bombers. 12 contacts, approaching from the northwest. He reached for his telephone to alert the night fighter controller, then stopped, staring at his screen. The 12 contacts had become 20, then 40, then 100. His screen was filling with returns, multiplying exponentially, spreading across the display like an infection. He tapped the screen, thinking the equipment had malfunctioned. The contacts continued multiplying. "Herr Leutnant?" His operator's voice carried an edge of panic. "I'm seeing massive formations, hundreds of aircraft. No, thousands." Schneider grabbed the telephone. "This is Station 12. We have... I don't know what we have. The screen is saturated. Every sector is showing dense formations." Across the German defensive network, the same scene played out. Radar operators stared at screens that had become useless, showing so many contacts that tracking individual bombers was impossible. Night fighter controllers tried to vector their pilots toward enemy formations and found they were directing them toward clouds of aluminum. The Luftwaffe's sophisticated defense system, the network that had extracted such a terrible price from RAF Bomber Command, simply stopped functioning. The bombers pressed on toward Hamburg. For the first time in 3 years, they flew unmolested by radar-directed fighters. Flak batteries fired blindly, unable to track their targets with precision. Searchlights waved uselessly across the sky, unable to be directed to specific aircraft by radar. The bombing was devastating. The city burned. But for Davies and his crew, the miracle was simpler and more personal. They flew to Hamburg and back without a single fighter interception. Not one searchlight caught them. The flak, while heavy, was random and ineffective. They landed at 0330 hours, tired but alive. Davies climbed down from his Halifax and looked at the empty bomb bay where the window crates had been. 40 pounds of aluminum foil had done what millions of pounds of investment in jamming equipment could not. It had blinded the Germans. It worked. Two simple words that meant everything. The results from Operation Gomorrah were analyzed within 48 hours. Of 791 bombers dispatched, only 12 were lost. 1.5%. Normal loss rates for such a deep penetration raid would have been 6 to 8%. Window had reduced casualties by 75%. 75%. The numbers were almost unbelievable. Within a week, every bomber in RAF Bomber Command carried Window. The production order was massive. Millions of strips, cut and bundled in factories across Britain. Women in munitions plants worked around the clock, cutting aluminum, bundling it with thread, packing it into crates. The cost per packet was negligible, less than a penny. The cost savings in aircraft and lives was incalculable. The Germans were caught completely off guard. Their radar network, which had cost hundreds of millions of Reichsmarks to construct and maintain, had been defeated by something a schoolchild could make with scissors and foil. German scientists scrambled to develop countermeasures. They modified radar frequencies, hoping to operate at wavelengths that Window wouldn't affect. British scientists simply cut new strips to match the new frequencies. The modification took hours. The German frequency changes took months. They tried visual identification procedures, training radar operators to distinguish real contacts from false ones based on movement patterns. But in the chaos of a raid with thousands of window strips falling, visual discrimination was impossible. A real bomber and a cloud of aluminum strips moving on the wind looked identical on a radar screen. They attempted to collect window samples from crashed aircraft and bomb sites, analyzing the aluminum to find some unique characteristic that could be filtered out electronically. But there was nothing to filter. Window was just metal reflecting electromagnetic waves, the same as any aircraft. There was no magical frequency, no special signature, just basic physics turned against them. The impact cascaded through the German war effort. Night fighter losses mounted as pilots hunted phantoms instead of bombers. Flak ammunition was expended wildly, batteries firing at false contacts until their barrels overheated. The Luftwaffe's entire defensive doctrine, built around radar-directed precision interception, had to be abandoned. Military analysts estimate Window shortened the strategic bombing campaign by 6 months. It saved somewhere between 15 and 20,000 Allied lives. The RAF could now strike deep into Germany with acceptable losses, maintaining pressure on Nazi industry and morale while the invasion force prepared for D-Day. Eisenhower was briefed on Window's success and immediately ordered it adapted for American bombers. Churchill, in his characteristic fashion, remarked that the war had produced many weapons, but few so elegant as pieces of Christmas decoration that unmade German radar. The technology spread beyond strategic bombing. Fighter aircraft used Window to mask their approach during ground attack missions. Naval vessels deployed it to confuse German coastal radar. The Americans developed their own version, calling it Chaff, and used it extensively in the Pacific Theater. By the end of 1943, Window was standard equipment on every Allied combat aircraft operating over Europe. German radar operators learned to hate it with a passion that bordered on obsession. It represented everything that was going wrong with the war. The Allies' industrial might, their scientific creativity, their ability to take simple materials and transform them into weapons that negated Germany's technological advantages. German technical journals from late 1943 make fascinating reading. There's a sense of bitter frustration in their analysis of window. One report noted that the enemy has defeated our most sophisticated detection system with nothing more than what a child might use for an art project. The psychological impact of this technological humiliation shouldn't be underestimated. German confidence in their technological superiority, already shaken by encounters with Soviet T-34 tanks and British code-breaking, took another significant blow. The innovation changed how militaries thought about electronic warfare. Before window, radar countermeasures focused on power, jamming transmitters that tried to overwhelm enemy radar with raw electronic noise. Window demonstrated that cleverness could defeat power, that understanding fundamental physics and exploiting basic principles could be more effective than brute force. Post-war analysis revealed that Window's introduction marked a turning point in the air war over Europe. German fighter pilot diaries from August 1943 onward consistently mention the frustration of hunting targets that vanished into clouds of false contacts. One pilot wrote, "It is like trying to catch a particular fish in a school of thousands. By the time you identify your target, it has moved, and you are lost in a sea of meaningless signals." The technology became so widespread that by 1944, both sides used it routinely. German aircraft began carrying their own version, called Duppel, to confuse Allied radar during their increasingly rare offensive operations. The sky over Europe filled with millions of aluminum strips, a constant metallic snow that made radar operators' lives miserable, but saved countless air crews from death. Years later, in 1962, a BBC reporter tracked down Joan Curran in his small flat in Cardiff. He'd returned to teaching after the war, quiet and unassuming, living on a modest pension. The reporter asked about Window, about his role in developing a weapon that had changed the course of the war. Curran was uncomfortable with the attention. He deflected credit reflexively. "I wasn't special. I was just a bloke who thought about a problem differently than the experts did. The real heroes were the aircrew who had to fly into German airspace night after night, not knowing if they'd come back. I just gave them slightly better odds." When pressed about being rejected by the Royal Aircraft Establishment, about how his lack of formal qualifications had nearly prevented him from contributing to the war effort, his expression grew thoughtful. "The rejection hurt at the time, but looking back, maybe it taught me something valuable. The experts were all looking for complicated solutions because they'd been trained to think in complicated terms. I was just a schoolteacher who liked tinkering with radios. I didn't know enough to realize the solution was supposed to be complicated, so I found a simple one instead." He paused, lighting a cigarette with hands that trembled slightly with age. "The war taught me that sometimes the most valuable people aren't the ones with the most credentials. They're the ones who can see problems fresh, without preconceptions. The military, any large organization really, needs to make space for unconventional thinkers. Not just tolerate them, but actively seek them out. Because the next impossible problem won't be solved by doing what we've always done, only harder." Joan Curran died in 1979, his obituary running just 3 paragraphs in the local paper. It mentioned his teaching career and his work during the war in vague terms. It didn't mention that he'd personally saved thousands of lives. It didn't mention that German radar operators had cursed his name. It didn't mention that his simple innovation had helped win the air war over Europe. There's a small exhibit at the RAF Museum in Hendon, London. In a glass case, illuminated by soft lighting, sits a packet of Window. 26.5 centimeter strips of aluminum foil, bundled with cotton thread, weighing 40 grams. Next to it, a plaque explains how this simple device defeated Nazi Germany's radar network and changed aerial warfare forever. In his memoir, published posthumously, German radar pioneer Wilhelm Runge wrote about Window with grudging admiration. "We had created the most sophisticated radar network in the world, and the British defeated it with children's crafts materials. It was a profound lesson in the limits of technological arrogance. Sometimes simplicity defeats sophistication. Sometimes a schoolteacher with a notebook is more dangerous than a team of doctorate-holding scientists with unlimited budgets." The technical specifications of Window are now declassified and taught in every military electronic warfare course. But the real lesson isn't technical. It's about organizations and how they identify talent. About the danger of credentialism, of assuming that formal qualifications are the only marker of capability. About listening to ideas regardless of their source. Hitler's biggest secret wasn't his wonder weapons or his advanced technology. It was his system's complete inability to recognize and respond to unconventional thinking. And one rejected engineer with a notebook and a roll of aluminum foil exposed that fatal flaw. The strips of aluminum still fall sometimes, during military exercises, glittering in the sun like metallic snow. Pilots call it chaff now, dropped to confuse missile guidance systems instead of World War II radar. The technology evolved, but the principle remained unchanged. Simple physics, elegantly applied, defeating sophisticated systems. Joan Curran understood that. He understood that genius isn't always found in universities or research laboratories. Sometimes it's found in a garden shed in Cardiff, in the mind of a schoolteacher who loved radios and refused to accept that the experts knew everything. Sometimes the most powerful weapon is just an idea executed perfectly by someone nobody expected.